Right, the last couple of days we dealt with infinite limits, and we talked about the idea of slopes of tangent lines, equations of tangent lines. You had two sets of homework to do, page 138. You had some odds to do, which was infinite limits. Then 144 asked you to do a couple of the equations of tangent lines. Questions you have on anything with infinite limits? Any of those? Let's get a key idea with respect to infinite limits. Is our limit as x approaches infinity, and it doesn't matter if it's plus or minus here, of any constant over x to the nth power where n is going to be greater than the value of 0. This will equal a value of 0. And this is the key idea to remember as you work yourself through infinite limits. This will always be true. So if you can get in the form of some constant over a variable, you'll be able to solve our solution for that. Number 19, we have square root of t. Limit as x approaches infinity of square root of t, because this t is approaching infinity, plus t squared over 2t minus t squared. Did you ask that one because it's the right one?
Oh, yeah, it's like I have no clue how to do it.
Well, if we take a look at this, what you start looking at the square root of t in there, well, how can you change the square root of t to an exponent? What's square root of t as an exponent? T to the 1/2 power. T to the 1/2 power. Okay, what we talked about yesterday is we're using the idea of equivalent fractions with dealing with that. With equivalent fractions, you're reducing a fraction down or multiplying. You're either dividing or multiplying the numerator and denominator of your fraction by the exact same thing, and that gives us that equivalent fraction. Well, what we talked about yesterday was, well, let's take a look at our largest degreed variable. Our largest degreed variable, well, I have t to the 1/2 t squared minus 2t, or 2t minus t squared. What's our largest degreed variable? T to the what power?
Squared.
Squared. So we're going to take and we're going to divide through numerator and denominator by this t squared. So each and every one of our terms is t to the 1/2 divided by t squared plus t squared divided by t squared, 2t divided by t squared minus t squared divided by t squared. We're dividing every one of our terms by the t squared. Well, if I look at, we have t to the 1/2 over t squared, we have to subtract our variables, our exponents. Now, and this is what I talked about yesterday also, as you get more and more comfortable with this, you can do this as a mental operation. You don't have to write this out each time. You can show me what you're dividing by over here, but mentally you should be able to go from here down to here as you get more and more comfortable with this. Now, I have t to the 1/2 and I have t squared on the bottom. What do we have to do with our exponents when we're dividing? Subtract them. You subtract them, and if you want to keep it positive, you put it where the largest exponent is. So we have 1 over 2 minus 1/2, which is 3/2. So we have t to the 3/2 power. or 3 halves power, plus 1. Let's see, we have 2 over t minus the value of 1. As we talked about yesterday in our properties of limits, you could put the limit anywhere you want. But once again, the mental math is you're going to take the limit of each one of these terms here. So mentally, you're taking the limit of each one of these terms. And this is something that you can do as a mental math also. You don't have to write this step out. But what we fall into now is we fall into utilizing this property with respect to infinite limits. With this property with respect to infinite limits, if I have a constant over t to any exponent, just so it's positive, I'm going to get a value of 0. So we are left with 0 plus the limit of a constant is going to be that constant. So we have 0 plus 1 over 0 minus 1. So we're left with 1 over negative 1, which is negative 1. When I have square roots, it slows down how fast our y value is going to get. When I have a larger exponent, more than 1, it's going to increase the speed of how it's getting to the value of infinity or value of 0. Okay, what we're going to do today is we're going to take a look at graphically what are the effects of limits. What effects does limits have to our graphs? What effects our limits have to our graphs? If we had 2 scenarios with our discontinuities. When we had discontinuities, whatever makes our denominator equal to 0, when we have the discontinuities, we had 2 scenarios. One scenario is we had where we could eliminate the discontinuity. Limit as x approaches 2 of x squared minus 4 over x minus 2. This was a removable discontinuity. If I try to plug it in, go through my progression in regards to limits, I don't have any radicals there or logarithms, so it's defined coming in from that direction. So my direction is not a big deal. But if I try to put in the value of 2, I get 4 minus 4 over 2 minus 2. Can't do it. So we factored, we canceled, we subbed. We factored, we canceled, and then we subbed in, we got a value of 4. We came down to a value. But if you use 1.9, 1.99, 1.999, 1.9999, you get closer and closer to the value of 4. You never achieve it. Once again, we talk about that delta. You get that delta away from, from 2. You get that delta away from 2. You never quite achieve it. You have that 2 plus delta, 2 minus delta. You have that 1.999999999. You have a delta of 0.000000001. Okay, you're getting close to it, but you're never quite achieving it. We get closer to this value of 4 plus or minus the epsilon that we talked about. So you're getting closer and closer and closer and closer to the value of 2 on your x-axis, and you're getting closer and closer to value 4 on your y-axis, the question is, graphically, what's going to appear? And what's going to appear on our graph? Well, going back to just linear ideas, if I ask you to graph x is greater than 3, just graph x is greater than 3. Not throwing a limit in there, not throwing anything in. I'm just saying x is greater than 3. Preston, what would this graph look like?
Open circle, and all the way to the right of 3.
All the way to the right of 3. So the values that work for this is x that are greater than 3. 3.00000000001 is just greater than 3. 3.0000001 is just greater than 3. We're that small little increment away from the value 3. But when we hit 3, we have equality. So we're trying to get that delta away from 3, if we want to think of it that way. Well, what appears here is an open dot. Well, what's going to appear when I'm taking a look at my function now, x squared minus 4 over x minus 2? The result will be an open dot. The result will be the open dot on the graph at the discontinuity and the limit of the function at the discontinuity. So you're going to get a limit at the discontinuity, or you're going to take the limit as you approach a discontinuity. If it's removable, what you're going to get is you're going to get that open dot, because as we've talked about limits throughout all this information we've talked about before, you get that delta away from the value, but you're never achieving that value. We're never achieving the x value of 2, even though the first property of limits is substitution. You just plug it in. That goes to the idea of the word approaching. When you say the word limit, you're saying your limit equals the value, a specific value. What is understood mathematically when you're talking about the idea of limits, limits means even though you're saying you're equaling a value, you're approaching a value. The second thing we talked about was an unremovable discontinuity. Limit as x approaches 2 of 5 over x minus 2. We try to sub it in, we get 5 over 0. We try to factor cancel sub, we can't do it. So what was our solutions when we had that? When we couldn't remove the discontinuity? Yeah, infinities. Our solutions initially was a positive and negative infinity, and then we put our directional ideas here with our value. Then we could signify if it's positive or a negative infinity. Well, as x gets closer to a specific value, y gets bigger and bigger and bigger, or bigger in the negative direction. So we're approaching our infinities. What occurs there? Well, what will occur there is a vertical asymptote. We will have a vertical asymptote on the graph at the value of the unremovable discontinuity. So graphically, if we can remove the discontinuity, we're going to get an open dot there. If graphically we cannot, or algebraically we cannot remove the discontinuity, then we're going to get a vertical asymptote on our graph. The limits for the infinite limits that we just talked about. What is occurring now with infinite limits? If we take the limit as x approaches infinity of 2x plus 3 over x minus 2, and we take a look at this infinite limit, we'd have to divide through by what here? What would we divide through by? What's our largest degree x by the variable? X to the what power? X. Just x. So we're going to divide top and bottom by x. So we would get limit as x approaches infinity of 2 plus 3 over x and 1 minus 2 over x, dividing through by x. Anything over x is turned to 0, so we get 2 over 1, which is a value of 2. Now, as x gets bigger and bigger and bigger and bigger, the y value is going to approach a value 2. Once again, it goes back to our basic definition of limits. As x approaches a specific value, what does y get closer to? Well, as x gets closer and closer and closer to positive infinity and beyond, y gets closer to 2. But we'll never achieve it. We'll never achieve it. Well, if we take a look at our graph, we have y equals quantity 2x plus 3. Is that what I had? 2x plus 3 and x minus 2. And x minus 2. Divided by quantity of x minus 2. My window, I stretched it way out there. So if I take a look at my graph, as it gets closer and closer out there, my x value is very, very large. I flatten out at the value of 2. We flatten out at the value of 2. If I take a look, here's my value 2 on my graph. I just flatten out. And this is going out to millions out here. So on my graph, what I achieve is I achieve what is called a horizontal asymptote. A horizontal asymptote is located at the location of the limit of the function as it approaches infinity and beyond. What we are saying is our x value is getting larger and larger and larger. My y value is going to get closer and closer to value 1. Once again, when we look at the idea of limits, we're saying, yes, we have equality there, but really what we have is we are approaching a value 2. We will never achieve a value 2. For this function right here, okay, I will never, ever, ever equal a y value of 2. I'll get closer to it, but never equal it. Well, the last thing we have with respect to an asymptote are called oblique asymptotes. An oblique asymptote. If the limit as x approaches infinity of a function equals a constant divided by 0. The function will approach infinity but will be asymptotic. When we talk about an oblique asymptote, this is a slanted asymptote. It has slope. So when we talk about an oblique asymptote, we have a slope. How we approach or how we figure out our oblique asymptote. It will occur at the quotient. We take a look at the quotient of the function. So what we're going to do is we're going to transform this function here and make it look a little bit different. Rather than look at it in this form here, we're going to look at it in, well, what would happen if I would take x squared plus 3x plus 2 and divide it by x minus 1? What would happen? And we'll deal with that down here in a minute. Okay, if we take a look at this function here, x squared plus 3x plus 2, let's determine what our x and y intercepts are going to be. Well, the y-intercepts is a lot easier of the two. Y-intercepts occur at your x equals 0. So if I put 0 in for all my x's, I have 0 plus 0 plus 2, 0 minus 1. X or y-intercept would occur where, Preston?
1.
Putting 0 in. 0 plus 0 plus 2. 0 minus 1.
Oh, negative 2.
Negative 2. The x-intercepts are rational expression. Once again, our y-intercepts are determined by where y is equal to 0. So we're determining what this makes this equal to 0. But when we're talking about a fraction, we have a numerator and denominator. What makes a fraction equal to 0? We have a numerator function, we have a denominator function. Is what makes the numerator equal to 0? Because our discontinuities occur where our denominator is equal to 0. So we take a look at our numerator. If I have 0 divided by 5, I get 0. If I have 0 divided by 7, I get 0. 0 divided by 20, I get 0. So whatever makes our numerator equal to 0 will make our function equal to 0. So we take a look at our numerator, which is a quadratic equation. X squared plus 2x, or plus 3x plus 2, which we could factor down. So go ahead and factor it down. And solve for x. No, what did it come up with?
-1, negative.
We have x plus 2 and x plus 3, or x plus 1. So we have -2 and -1. Discontinuities. Discontinuities, whatever makes our denominator equal to 0. Preston, what makes our denominator equal to 0?
1.
1. So we have a discontinuity at x is equal to a value of 1. Now we have to determine at this value of 1, do we have a vertical asymptote or do we have an open dot? So we can take our limit as x approaches this value of 1. And I'm going to use my factored form already because we did it up there for the x-intercepts. We have x plus 2 over x plus 1, or x plus 2 times x plus 1 over x minus 1. Can we factor cancel sum? Can we remove the discontinuity? No, we can't. Because we can't cancel out the x minus 1s. So it is unremovable. The discontinuity is unremovable. So if we have a discontinuity that's unremovable, what do we have? An open dot or a vertical asymptote? We have a vertical asymptote. So we have a vertical asymptote at x is equal to a value of 1. So we have to find our limit as we approach infinity of our function now. Well, if I throw in an x squared, if I divide through by the x squared, we're going to divide through by our x squared. We have 1 plus 3 over x plus 2 over x squared. What we're left with is we're left with a value of 1 plus 0 plus 0 over 0 minus 0. We're left with 0 over, or 1 over 0. So we do not get a value. But we can still find an oblique asymptote. If I get a constant over 0 when I do my infinite limit, I will get an oblique asymptote. If we use long divisions, two things will occur here. The remainder is going to still approach a value of 0. The graph of the function will approach the dividend minus the remainder. So what we're going to do is we're going to look at this function up here. We're going to transform it because it's asking us to divide. When we have this fraction bar, it's asking us to divide. So we're going to look to transform this into a different look. So we could do one of two things. We could take the x minus 1 and divide it into the x squared plus 3x plus 2. Or if we remember back to our synthetic division. If we go back to our synthetic division, we'd have the 1 in the box, because we're divided by x minus 1, so we put the positive 1 there, and use our coefficients 1, 3, and 2. I know I'm stretching the brain back to a year ago at this time. We can drop our 1, we multiply 1 times 1, 3, we get a value of 4. We multiply by 1, we get a value of 4, we get a value of 6 there. Or if you use your long division, we'd have x squared minus 1. We have to subtract, change our signs. So we have 4x plus the value of 4, 4x, drop our 2 down, minus 4, change our sign, so we have a 6 there. This is our remainder. What we have transformed our equation into is the limit as x approaches infinity of x plus 4 plus 6 over x minus 1. As x gets bigger and bigger and bigger, y is going to approach this. It's never going to achieve. Well, if I take a look at this value right here, as x gets bigger and bigger and bigger, 6 over x minus 1 goes to 0. Just looking at infinite limits. As x gets bigger and bigger and bigger, and this is what we're asking here, as x gets bigger, y is going to approach x plus 4. As x gets bigger, y is approaching x plus 4 plus 0, because this will go to 0 here. So what this gives us is this gives us what is called an oblique asymptote. At y equals x plus 4. So if we take a look, I know I didn't leave much room for you there. If we take a look at a graph here, we have a vertical asymptote of x equals 1. Our vertical asymptote of x equals 1. We have an oblique asymptote at y equals x plus 4. So if I graph y equals x plus 4, I have a y-intercept at 4. I could go up 1 to the right 1. And we get our oblique asymptote. we have x-intercepts at -1 and -2. And we have a y-intercept at -2. Now, if we take a look, we have to contain these points, and we have to be asymptotic to this. Okay, so the first half of our graph is fairly simple to deal with, which is this section right here. I'm going to be asymptotic to my vertical asymptote. I'm going to come up through these points and be asymptotic to my oblique asymptote. If we take a look at our limit as x approaches 1 from the right of our function, which is x squared plus 3x plus 2 over x minus 1. As x approaches 1 from the right, and we could factor this to x plus 2 and x plus 1. As x approaches 1 from the right, this is positive, and x minus 1 is also positive. So this will tell us that we're going to go towards positive infinity, which takes us up to this direction here and allows us to be asymptotic here. These will be our working notes on Monday. Okay, go through a couple of these problems. And we'll spend a couple of days on this because obviously there's a lot of stuff here. But it's the effects of what happens to limits. Limits guide our graphs, what we deal with our graphs. So it helps us out being able to handle our graphs, especially with rational expressions, working with the idea of limits. Okay, work through some of the problems. I post solutions. I'll post some solutions. See what you can come up with. Okay, once again, this will be our working notes on Monday. Say hi to Trevor. Wave to him. Wave to him.
Good morning.
Hi, Trevor. How we doing? We miss you.
He probably saw as soon as the lesson's over, he probably clicked right off.
Yeah.